this is Armagan. If I'm not wrong, Hassan teach me.
Yeah.
He will show us how he will use the browser as an amplifier to the sound of his Fender guitar. I heard some nice noises of music. You will decide. Yeah, just give a warm welcome to the guy, okay?
Wow. Okay. First of all, I really like the environment here. It's like home, and like I have just friends who came over to talk about WebAudio. I don't know why they would do that, but apparently you are interested in this thing, so thanks for coming again today. And yeah, I'm gonna code some stuff, play some guitar, code a little bit more, and in the end, rock and roll. You mostly saw the songs that I prepared for you today, and I hopefully will be able to perform them to your expectations. Before we start, I want to show you what a real pedal board looks like in real life. This is what guitarists use all the time before their amplifiers to make music. You must have seen these in concerts, right? Like they always have this huge rack in front of them on the floor. Well, it's called a pedal board, and yeah, the idea is each of those blocks are, they are sound modifiers. In some way, they take the guitar signal as input and apply some analog circuitry, digital circuitry, some signal processing, depends on the pedal, and transforms those signals to something that's nicer to hear. Maybe add some reverb, add some echo, or delay, I don't know, modulate the sound so that it feels like it's coming from outer space or from somebody's gut. Or loop it so you play something for like 4 seconds and then it keeps playing so that you can play on top. Or distortion, that heavy metal sounds are also done by these little boxes. So this is what it is in real life. And 5 years ago, when the WebRTC group decided to include a audio capability to browsers, I said, well, I'm a developer, I also play some guitar, and I actually like to build these things in real life as well with electronic circuits, so why don't I combine these things? And yeah, I decided to do an open source library called pedalboard.js, and basically it looks like something like this. You probably already saw it, but the idea is we transform the boxes over here into their digital equivalents that are done entirely in JavaScript. So, well, maybe that's not true. JavaScript is what you interact with, but obviously it's the C++ APIs or maybe sometimes assembly code, optimized code in the browsers that are executing your commands. But the idea is each of these boxes include some logic in themselves to modify the sound. So you can just plug your guitar into your computer through whatever port you find, because some ports are really scarce these days. And yeah, you just play. You just need your browser. You don't need a special software. Normally people use software for like $300, $400, and when you get expansions, it just grows more and more, and that's not, that's not pocket friendly. So, well, that's their business model. That's how they make money. But since we're dealing with open source, we don't really have to make money. Although it would be really nice if somebody said, here's $1,000 for this library. But yeah, the idea is it's something that you can try to, maybe when you want to learn guitar or when you want to learn how these pedals work. It's just a free alternative that works everywhere. And yeah, I will also talk a little bit more about that later. But this is the actual beginning of the presentation. Who am I? I'm Arman Amcalar. I work here in Berlin at Unu GmbH, which is a mobility company, a mobility startup. We are building electric scooters and more mobility solutions for the future. They're really cool. And I also lead an organization, a voluntary organization called Lonja, which is a craftsmanship guild, software craftsmanship guild for women. And yeah, I'm also heavily active on open source community. I have a couple of different libraries that range from front-end libraries to brain signal processing to microservices, to code generators, to chatbots before they were cool, and yeah, a lot of other stuff available on GitHub, around more than like 100 repositories. Also recently I started teaching JavaScript in Women Tech Makers Berlin, and I have some students here today with me, which is really a huge honor for me. Yeah, and I think we're kind of doing okay there as well. At least I'm really, really satisfied with the number of people that we have. Okay, so let's start with what WebAudio is. Do you know what WebAudio is? Raise your hands. Cool. Okay, raise your hands if you played with it. Cool, that's great. So WebAudio is an API that is designed to enable huge voice or sound applications within browsers. Initially, they thought it would be really cool to have a audio engine for 3D games because WebGL is a thing, and you know it makes sense to have 3D audio when you're moving around a scene in WebGL application or a game. It would be nice if there were Dolby surround sound, or if you could play with the duration or the pitch of different sounds or voices. And then obviously they thought, well, that's a good start, but actually we can do a lot more. And it actually started in, I guess, I don't know, around 2011, and 2012 we saw the first implementations in Chrome and in Firefox, and it was huge. Initially it couldn't do much, but over time they added great features. And it's basically a JavaScript API that's available right now in every browser, in every major browser, that lets you get some sound from any sound device that is attached to the computer, or a file, or you can actually create sound. So you can do synthesizers. Actually, if you played with some Google Doodles, the interactive logos on Google's homepage, most of them are done with WebAudio API, especially the ones that include sound, where you can hit the notes, and there was a special one for Move that was really good, where you could attach some of those boxes with cables and then change the synthesizer. It was really good. But yeah, obviously the engine is native, so there are some discrepancies between browsers because not everybody is sharing their code, their native implementations. So, but they are really working hard to iron out the differences in the behavior of the API. So it gives you a very nice API to work with. And yeah, again, you can do 3D sound processing applications, sound production applications, like that was on my screen before. GarageBand is such an application that lets you, bring in different sounds and play some instruments and make a mix out of it. Or you could do video applications where you also put a video track and then, give it a background music or some sound effects. So it's basically endless what you can do. People use it for voice training, for tuners, or art installations. That plays really well with WebGL. And when you have some external sensors, you can really create dynamic music that responds to people's movements, or any like ambient light or anything. So yeah, anything you can imagine about audio is actually implementable via WebAudio, via JavaScript, and it's amazing. It's really simple. So some basics of WebAudio. Everything starts with a source. You have to have either a file source, again, or an input device like a guitar or a microphone even, or a WebRTC call, for example. That also passes so that you can do interactive applications. Actually, I also did one, and I'm gonna present it to you. And then basically you add a network of nodes. I'm gonna talk about some of those nodes in the following minutes, but you attach different sound engines. Like the simple one is the gain, which changes the volume of the input signal. It's, you can do it 0, 0.5 for 50% or 1, or actually even more, so that it increases the incoming signal, which is already useful. You can have a delay node, you can have a filter to, I don't know, like an equalizer you use in your audio applications or in your hi-fi, is it called? Yeah. So it's very, very intuitive. It's very simple. Normally, in native applications, everybody writes raw algorithms for each of these things. Like if you want to do a filter, you have to know the math behind it. You have to know how that filter should be implemented. But in JavaScript, it's just a type to the filter node. So when you give it low pass, it becomes a low pass filter. When you give it a high shelf, it becomes a high shelf filter. Just by changing a string value, you can change the behavior of the filter, and then you can obviously change every parameter, every frequency, and actually a lot of other parameters just over JavaScript, and it's live, it updates live. So it's really, really simple, and we'll see some code in the coming minutes. But yeah, the idea is for example, the guitar has a single output, it's mono, it's not stereo. So what you do is you can split it into multiple tracks, multiple channels, and then process them differently. And what we see here is there are two parallel effects. One is the delay effect that maybe delays the sound a little bit or adds a second copy of that sound, 300 milliseconds later or 1 second later to create an echo effect. And then on the other hand, you have a big quad filter. The type is not there, so it could be anything. Maybe it's a low pass filter, so you don't hear huge noises, and you filter out the upper end of the spectrum where actually no human hears anyway. And then you can merge those channels, those different tracks, and have a target, which is your headphone jack in this case. Or, well, I don't know, it could be anything. It could be another application. And most importantly, again, it could be a stream, a WebRTC stream, which means you can actually do audio processing locally and then send it to your friend over the network or your friends over the network, which is a huge opportunity for interactive applications. So what kind of components there are? Everything starts with an audio context. I will talk a little bit more when we get to the demo page, what an audio context is, but basically it's the bed, the namespace that includes everything. So you first create an audio context and put everything in. It's like a canvas for drawing something. Anybody familiar with the canvas on Web API? Yeah, cool. So it's like a canvas for audio. You usually have one audio context where, well, you can actually have multiple, but it doesn't make much sense. So you have one audio context. You can have an offline audio context, which could be used to basically render some MP3 files. So that you don't have to stay in the browser all the time. You can, create pedals, record something, and then click save, and then get it exported as a WAV file, as a WAV file, or you could do offline processing for converting between audio formats, or again adding reverb delay to your previous recordings. You have the gain node, the delay node. You have something called a convolver. Anybody familiar with the term convolution? Okay, it's a signal processing term. You basically give it an infinite impulse response filter, which is used to simulate room sounds, or an environment like a room, a hall. It could be a chamber, a forest. Any environment transforms the sounds on its own. So the convolver node actually lets you use any IIR filter that you may have, and usually in audio applications you do have those, like for reverb effects as well. And in guitar applications, the cabinet sound, cabinet is a box, right? It's an environment, and it has a very, very unique sound. So you need to capture that to be able to, create or reproduce a similar signal processing chain. So you have an analyzer node which gives you visuals or data for any visuals about your signals. So you can see which frequencies are there. You can, you know, anybody used Winamp? Winamp, yeah. That our old friend. Yeah, there's some young face, yeah, young faces here. But you know, we had the visualization in Winamp where it showed some bars, and you know, according to the music, the bars went up and down, and it was green and red. Basically, you can do a similar thing with 10 lines of code in JavaScript with WebAudio API, which is cool. Like, it's amazing. Yeah, you have a lot of other stuff, and then lately they added something called an audio worker, because the applications for the browser got really serious, and the single-threaded architecture didn't really serve the audio applications anymore. So they said, okay, it's like a service worker or a web worker. So it basically creates other threads for you to process data. Because people started, hey, I want to create my own sound. I don't want to use your built-in libraries. So just pass me an array of values for each captured signal, each amplitude value, and I will implement the algorithm myself. So actually, we have come full circle. People started with simple APIs, and they abused them, they overused them, and then it basically went back to the beginning, and people now write their own algorithms again in the browser, and they run these in those audio workers, which are separate threads, so they are very fast. They are not in the DOM, and you can have multiple of them. If you have 8 CPUs, you can have 16 different audio workers, and it wouldn't be a problem. You would still be able to do real-time processing. So yeah, some really serious applications are being done with WebAudio. Okay, so what does pedalboard.js do? It is one of the first open source libraries for WebAudio. Basically, it was there before WebAudio was finalized, and the implementation was finalized. There was no sound input, for example. You could only do some of the processing, and if you go to the commit history like 5 years ago, one of the first commits is to add audio input from Flash. So you could do that because Flash could capture audio from microphone, right? And what I did was I captured the raw audio signal from Flash and somehow made it available to the browser, and then the nodes would kick in. There were some delays, so like up to 500 milliseconds or a second, because Flash was really slow. But yeah, a year later they added real input, so basically we could replace it. So it's GPL licensed. I wanted it to be available to everybody, and like any other contribution should be merged back to pedalboard.js. It's really well documented, both inside the source code and in the README, and the API is really cool. So you have pedals, you have pots, you have switches or LEDs. Like the components on each pedal is available to you in the framework, so that you can just combine those and create your own pedals. And I will actually demo some code. Anybody familiar with Google Closure Library? Google Closure Library? Nobody? Oh, come on, this is GDG, right?
Closure, like with a J, or?
No, that's the language.
Yeah, no, Closure Library, never heard of it.
Yeah, so this is the best JavaScript library out there. And I have no affiliation with Google, okay? I don't really mind, and actually like nowadays I don't use Google Closure Library because some new kids on the block don't like it or know it. But it's the best JavaScript library out there. It's the most performant JavaScript library you can ever imagine in your life. It's really hard to use.
You're trying to start a war, or?
Yeah. Yeah, basically, it is what Gmail, Google Docs, and any other major Google software on the web is built with. And Gmail worked in 2006, right? It's built with Google Closure Library, which is a little bit older library actually. But it's still actively maintained, and it gives you the best compiler out there. TypeScript compilers or other compilers that are from Facebook, etc. They're just starters, they're babies, newbies. Google Closure Compiler was there like since 10 years. And it's amazing. It type checks your code, it makes sure your code is sane, type safe, and actually also improves the performance of your code while compiling, like up to 20%. That's amazing. So if you don't know Google Closure Library and Google Closure Compiler, just check them out. They are really lovely. And yeah, basically this thing is built on Google Closure Library, and it uses a model view model architecture. Anybody familiar with that? Model view model. That's good. It's one of the best architectures to do user interface applications, and nowadays all the frameworks in JavaScript use MEVM. Even if they don't know what they're using, it's actually MEVM. And yeah, pedalboard.js is one of those. So what do we have? We have a stage, because without the stage, a guitarist is nothing, right? You have to have a stage. Even if it's your own bedroom, you have to have a stage to be able to play. So stage is actually the thing that gives you the audio context, because audio context is an unfamiliar name. It's hard to understand, but everybody knows what a stage is. So you first start with a stage, and then you have a board, a pedal board. You can have as many pedal boards as you like. And you have some boxes, which are actually empty, which means kind of abstract classes. So you have to subclass box and implement your own pedal boxes. You have foot switches, LEDs, pots, file input, stream input, and a lot of other pedals. Well, oh yeah. So a box comes with a foot switch that you can press to toggle your pedal. It has an LED to show if it's on or off, and a potentiometer for volume, so that you can change the volume of the pedal. That's out of the box. Pun unintended. But yeah, for file input, you have to rely on the browser's native file support. So it can support MP3. Some browsers don't support MP3. So it can play WAV or OGG or whatever the browser actually natively supports. Or you can have a stream, again, any audio stream, or a WebRTC stream, and you can do funky effects with WebRTC. Anybody used WebRTC to do video chat? Yeah, video chat in the browser works with WebRTC, unless you install a third-party plugin, which you shouldn't. Like, the browser should be self-sufficient, and it should basically do everything you need it to do. But okay, then we have some pots, potentiometer. Anybody familiar with the term potentiometer? Okay, it's the knobs that you play with. Like here, this is the sound knob. It's the potentiometer. Basically, it's a device that changes the resistance. So you have a circuit, you have a voltage, and you have a resistance, and potentiometer actually changes the resistance value so that you can, fine-tune the volume or change any parameter, any effect that you want. There are two types. One is linear, one is log. This is a little bit deep into electronics and electronics engineering, but logarithmic potentiometer is used for audio applications. So it's a nice information or knowledge that you can sell when you go out with your friends. Hey, you know what they use for those volume knobs? It's different. The volume knobs are unique because the human ear actually has a very unique structure. If you double the amount of volume that you have on any file, you actually don't hear it doubled. Your ear actually tunes it down a little bit, so it's actually a logarithmic graph. So for a sound to feel double the amplitude, double the volume, you have to actually increase it by 10 times. That's how logarithmics work. And so logarithmic potentiometers make sure that when you have a pot like that, 0 is actually 0, 10 is actually the full volume, but the most important one is 5, the in-between value, actually represents half the volume that you hear. So let's say a potentiometer is a resistor, right? Let's say it's 1000 ohms. Anybody familiar with the term ohm? Cool. It's 1000 ohms. We call it 1K. So at full level, it's 1K, and at 0, it's 0. And at half value, it's actually 0.7. And that's normally, if we were not human, or I don't know, if we had a different structure, that would be 70% of the volume. But when you put it at 70%, we actually hear it as half as loud. Therefore, you know, this logarithmic potentiometer is used for volume applications extensively. And every other parameter is almost linear, because when you put it to 5/10, you want it to be 50%, and you want to, you know, have the filter to be at 50%. But yeah, it's kind of a weird detail on how human ear works in psychology and in physics and in electricity. So we have foot switches and LEDs. All right, now it's demo time. Yay! Wait. Don't clap at. Maybe I'll be very bad.
Okay.
But I actually okay. Oh, we have half an hour almost. That's perfect. We have a lot of time because I want to show you some code, right? If I can find where it was.
It's in the browser where you have the presentation.
Is it? Yes, it is. Okay. Great. So let's start from scratch and let's do some stages and some pedals, and also we'll look into some code. I don't know, would you like to see the details of one of these pedals? Like how it's perfect. All right. Good. Then maybe I first show that. So one of the coolest things is, and yeah, this is actually how the code looks. So it doesn't use ES6 because there were no ES6 5 years ago. It's ES5, and it uses the Google Closure library to even do object-oriented programming, like to extend the class. But yeah, any JavaScript developers here? Cool. Anybody who wrote prototypes like this? Okay, not everybody, but you are lucky. You are the older generation, and you know the real deal. All right. So this is actually, you see, this is a reverb pedal, and this is all you write to have it. It extends from the convolution pedal. So what is a convolution pedal? Let's go and see that. Okay, it extends from box because you remember the box is the parent class, right? It is the empty box that holds everything. So a convolution pedal is actually something that has some special model, view model that goes with it, that includes a convolver node. So a convolver node has a impulse response filter. So this is very deep in the framework. That's why there's a special pedal called convolution pedal, so that you don't have to write this code. But what I do is I load a wave file that includes an impulse response filter, which defines the characteristics of an environment, like again the cabinet. So I use it to simulate a cabinet, a guitar cabinet. And well, I load the wave file over XHR, decode it, and it gives me an array buffer, if you will. And well, that is all I need to include convolution in my library or in my pedal. And reverb actually extends from that. And yeah, basically the default impulse response filter is already a reverb filter. So this is the code that's required to write a reverb filter. But let's go into a little bit something different, like a volume, right? The models are what have the logic, and all it does is, it creates a gain node, and it just sets the value of that gain. And it changes the volume. So I will actually demo this a little bit later in the browser, so we will see how it actually works. But let's go to something a little bit more complicated, like an overdrive. An overdrive is something that creates the distortion sounds that you hear in rock tunes. And we have a method called createPots. It is an entry point where you actually say, hey, I have a volume knob, or I have an overdrive knob, or tone, or whatever you want. And I actually have two. One is the drive, the other one is the tone. And if you remember, the volume is already there from the box, so I don't have to write that. But yeah, it is designed so that it's humanly readable. It says this is a drive pot. It's a logarithmic pot, logarithmic potentiometer, and whenever the value of that potentiometer changes, just set the drive of the pedal, or when the tone changes, just set the tone of the model. So what does the overdrive model do? This is fun. It has a low-pass filter. As I told you, it's a B-quad filter, and all you need to make it a low-pass filter is just to write low-pass in string. And you can change the value of its frequency. So it basically decides how thick the sound will be, or how clear the sound will be. And we have something called a wave shaper. This is where some math and signal processing is involved. Basically, WebAudio API passes the input signal through this code, which is actually just 33 values of multipliers, and you say, okay, I distort the wave, I shape the wave. So you basically give it a group, an array of numbers, so every point, every value in the incoming signal, every point in time, every sample is multiplied by these values so that you can distort the signal. If the multipliers are 1, what do you get? The same signal, right? Because you multiply it by 1. It's as easy as that, actually. But then you can do some weird math, and obviously I didn't come up with this math, but I just experimented with it and hacked it, and also found it online, like an inspiration online for an equation. And yeah, basically you give it a weird shape, a weird signal, almost like a noise, and then in the end you hear that distorted sound. It's basically distortion. And yeah, all that's necessary, because some of you were here when I first did the sound check and you heard me playing a distorted guitar, right? Well, this is like this 10 lines of code that gives you that overdrive sound. And again, it's in JavaScript. So you can play with it however you like. You can create your own pedals, you can create your own distortions to look for that vintage tube amplifier sound. If there are guitarists here, they know that that is the hardest thing to get with software, because analog amplifiers which use vacuum tubes are really, they have a very unique sound. And yeah, basically it's hard to imitate that with an equation, but you can try. I definitely tried. That's what we hear. But yeah, this is basically as simple as that. Whenever the tone is changing on the front end, whenever you drag the pot, or from the console you say, hey, overdrive.setTone, and we'll do that, the frequency value of the low-pass filter changes. So it's really easy to read. You don't basically write much code. And everything comes together really nicely in this model, basically, because you can do anything you want with these simple circuitry. But let me show you something a little bit complicated. Like a chorus model. A chorus model is obviously the view model of a chorus pedal, and it makes the sound, it changes the sound so that you feel like 5 or 6 different people are actually playing, or it gives you kind of a orchestra or chorus, or yeah, that kind of space in your sound. And therefore it actually includes more logic. Obviously, you have several different nodes. I at first was really afraid that this would cause performance problems, but apparently WebAudio API can have hundreds of nodes and it doesn't matter because they are all implemented natively in C++ and optimized when the browser is compiled. So it's super fast. And all I do is I have some nodes, I connect them together. I won't go into the details because it's really complex, but you create oscillators, you create delays, and somehow you modify the input signal so that the human ear thinks that there are multiple sources. And you know, it's not just one source, but there are multiple sources that are playing at the same time, or you know, just singing like a choir. But yeah, it actually goes a little bit long, so about 70 lines, but that's it. And yeah, and basically we'll give you some nice chorus sound, and maybe I can now demo what these things are doing in the browser. Okay. The browser is here. All right, so I start with a blank canvas. This is kind of the stage, if you will. This is the horizon. And yeah. Okay. Anyway, so again, I start by creating a stage. Okay, that's the first thing I do. I do new PB. PB stands for pedalboard. If you didn't notice already. So I first create a stage, and then I do a render and I put it in the DOM. Obviously, the stage has to happen on the floor, right? You can pass it any DOM node, but since I like to be this kind of, you know, with naming weird, I wanted to name the div floor so that I could, you know, it feels a little bit fine. And then you have a context. So this context is required by this is the audio context that is on the stage. It's required by every pedal out there because they are adding nodes to this context. Basically, in the end, a pedal is some wrapper that adds certain nodes, WebAudio API nodes to the audio context. So you have to pass it around. And then you create a board, and then you set the board to the stage. So let's run this first code. Is it readable actually, or should I make it over there? All right. Because you're in the first row. All right. So we had the stage. I created the stage. I rendered it. I got its context because I will pass it around, and I created a board. And well, I did stage.setBoard. So you can have multiple pedal boards, and you can switch between them. When they're in the stage, you will hear the output. When they're not, basically they won't do anything. But currently the board is empty. This is one advantage over analog pedal boards. They don't tell you when they're empty. You have to look and see. But this thing actually tells you when there are no pedals on the board. So okay, let's comment out these and run the next one. So maybe let's start with the volume, because that is the first thing that I want to create, to be able to change the volume of the sound, right? So I run this, and actually you now have it here. Volume is a variable, and you can change it. You can do volume dot set level. Okay. Well, I thought we had an hour.
No, 45 minutes plus questions.
All right, perfect. All right. So you can do volume.level, and you can change the volume of the pedal. And then, in the end, well, since I need to speed up a little bit, let's uncomment everything and run it all, right? So we have the board, and then we have all the pedals here that I want to add: a noise gate, a tremolo, flanger, and then I do board.addPedals. That's basically all there is to it. And when you run the code, you see all the pedals are already added, and you can now change any knob here by like playing it with the mouse, and yeah, like this. Or you can actually do, you know, let's change it over the code. All pedals dot or square brackets 2 will give me the overdrive pedal, and then I can, you know, set tone 0.1, and you'll see it's already automatically updated on the UI. This is not so cool in 2017, but it was really cool in 2012. And it also changes the tone of the pedal. So let me actually show you how this thing works. Let's see, I also have some code here that's okay, so maybe this is also interesting. I have a stream input, and yeah, just a second later I reroute the stage, so all the cables within it, and yeah, let's refresh it, run it again. Yeah, so you have the sound there. Let me know if it's too loud for you. I can turn it down, because like this will be a kind of a show. Okay, so the first thing that I actually want to talk about is the noise gate. It's a very, very special pedal, and you'll understand why when I turn it off. Watch your ears. Okay, it's not that bad, but like this is the noise that you normally hear from a guitar, right? And there's a noise gate, and when you activate it, the noise is gone, and you can still play it.
Was it a 50 Hz noise or?
Yes.
Okay.
Because like the single pickups don't really work, and actually when you use two of them, one is the ground, so you get less noise, but when you use only one of them, you have this noise. And this is a very special pedal. It's kind of one of the best in digital pedals, not to brag, but yeah, it actually follows your signal, and whenever it detects a special noise pattern, it says, okay, like the volume is down now, it's like 10%, so that you won't hear it. But whenever there is a huge sound like this, well, it basically allows you to play that, because that's actually a signal that you want to play. All right, so let's get a clean signal here. Let's remove the delay and the reverb. And the chorus and the cabinet, so you can actually see the raw signal of the guitar, and you can appreciate what JavaScript is doing here. Okay. And tell me if there are any languages out there which can do this. And I put a cabinet, so it has a much thicker sound, it's an aura, and I put a reverb, so you can hear that it's going on, it's like an echo. Let's see what the chorus is doing. That's one of the most interesting ones. It's this very subtle, very nice sound. You know, originally it's like this. This is one guitar playing. And when you have a chorus, it's like, it's much nicer. Again, since it's one of my hobbies to buy every pedal out there and to play with them, I kind of fine-tuned these things to make sure that they are, that are really nice to hear. But then we have the overdrive, obviously. And you can play with the drive so that it's very subtle. Almost like 50s, and maybe if you add also a little bit delay to it. If you, yeah, kind of emulating the sound of. Okay, yeah. And maybe give it a little bit drive. Okay, not bad. Right? Great. We're not there yet. I actually had 3 different songs, but I already played all of them to you, so I'm just gonna play Johnny Be Good. Or if you have a favorite, I have Nothing Else Matters, the solo, the part that I love most, Johnny Be Good, and Take 5 from the jazz classic Dave Brubeck, I guess. Pick one.
Johnny, no.
Alright. Alright, then...
Maybe you can play all 3 of them at C bass.
Yeah. What pedalboard is, and yeah, maybe this is the final slide. So find it online, and the slides and the demo, and let's keep in touch. Thank you.
We have time maybe for 1 or 2 questions.
Yeah.
Okay, Andres.
You already said that I have a question about the web audio part actually. You said that the processing is done in optimized C++, but can you also use specialized hardware like DSPs or maybe even a Dolby Atmos processor or something like that?
No. Unfortunately, there are no intermediate ways to incorporate other plugins, or if it's hardware, of course, you can use it as an input, but if it's software, you cannot use it.
Okay.
Maybe having like remotes?
Not in pedalboard.js, but I also have another experiment with WebMIDI, and I also want to integrate it so that each pedal can learn some MIDI signals and you can assign them. I use it for image processing, but that would be really cool to have it in this one as well.
Is WebMIDI some part of WebAudio or?
It's another API. and it gives you total control over MIDI devices. Basically, you can do everything that a MIDI device can do.
And it's supported in the browsers already?
Yes.
So if I connect MIDI keyboards to my browser, I can already...
Yes. And you can connect to WebAudio and play real synthesizers.
Matthias?
Yeah, I wanted to ask you about delays here. Like, I don't hear much delay here, so it's obviously under the like magic 18 milliseconds or whatever it is, right? So has this been this way? It hasn't been this way all the time, but it has been this way since you have native input.
Yeah, exactly. So obviously Mac does it because the audio drivers are really well implemented, so there's zero input. On Windows you have a problem. You have to have special audio drivers to get zero latency. But yeah, the Chrome team and the Firefox team, and also afterwards the Safari team did an amazing job at optimizing that. So basically it's zero latency, and you can actually see that I could play to a real tune that's going on without much delay. It's because it's a nightmare, but yeah, it works. So we can use it on stage actually.
Are you using it on the stage?
Yeah, and the best part is you can set this up on like at your home and then go to the studio without bringing all those pedals or anything, and just ask the studio guy to open their browser, and you know you can you can just unload your pedals there and it will work, no problems at all. You don't have to carry anything other than your guitar. As long as you have a browser, it will work.
Can you make some kind of like a shortcut links to remember all my state and just send it to the studio guy in one link?
You could, technically it's open source, but it's not supported out of place.
Okay, thank you all.
Yeah.
So we want you to frame it, picture it, Thank you all.
Yeah, thank you.
Okay.
And I'll be here for a couple of more minutes to...
Yeah, you can find him outside, so chat with him.